Hello and welcome to day 19 of Advent of Code in F#. This is not a live coding video. This is a, hey, I spent almost half a day solving it, and now just I will provide you with the executive summary of my solution. So day 19 is monster messages. And long story short, they give us a grammar and a set of words, and we have to check whether which words are part of the grammar, or which words can be produced by this grammar. So we're back into parsing and formal grammars world, or maybe not for part 1, because we could just generate all the known strings in the alphabet. But for part 2, yeah, you kind of needed to write a parser for this grammar again. Yesterday I used fparsec, a library, but I spent way too much time on it, and I was not done with day 18 when I started day 19, because it took me that long to research. So I tried something else for day 19. I wrote my own parser. And if you solved part 1 already, you will notice that there's a hint in there for part 2. Yeah, there's this rule hint. You only need to handle this specific case. Do not build a solution that can handle any hypothetical combination, because there's some recursion in the rules for part 2. And there's like this green text saying this will be significantly more difficult. And I was accepted that challenge accepted. Let's try it. So I wrote a generic parser that works for every case, not just for these 2 loops we introduce. So yeah, let's take a look at the code. Or before we do that, let's take a look at this blog post by Scott Blashin of F# for Fun and Profit again, which is a very good resource, which I've already mentioned for F#. And this really explains what a parser is, what it looks like, what it does, what you can use it for. And I think this post even starts from first principles. Yeah, it's like build a simple parser, combine it into more complex parsers, and go, go, go. But actually the thing I wanted to focus on is this. So this is what a parser looks like. A parser is basically a function. This is what this gray block means. And it takes an input string, the stream of characters, and it returns like true or false. That's the evident bit, like, okay, yes, this parser parses the stream, or it doesn't. We can't find a match. But the interesting part is this, and it's saying, okay, I did my job, so I parsed my bit, and I had a match or not, but this is what remains of the stream. So the way I think about this is I see every parser as a little pac-man, and the string as the candy. And every parser like just nibbles everything it needs, and then there's the remainder. That's what it returns. So it nibbles what it needs, and it returns the remaining characters. So that's the theory of a parser. It's a pac-man function. So this is my code for day 19. Yes, it is. Again, I like to work with abstract syntax trees. I don't like to parse and evaluate at the same time. So the first thing I do is write a parser that parses this grammar we were given into something we can work with. So this is a type definition that can hold everything we need. So it's saying a rule is either a character or a sequence of rule numbers, or an alternative, which is 2 sequences or 3 sequences or whatever of rule numbers. And then I define something called the rule book, which is a lookup table for rules. So rule 1 is in key 1, and there we go. And then I start by parsing the different types of rules. And there's 3 types of rules. Let's maybe go to this one. Yeah, so this is the parsing function. It takes a line and it tries to parse every possible case. And then it dumps it into this, the option type you just saw. There's only one thing I think we haven't used before, and that's these magical things on the left-hand side. This is where we pattern match. This is called an active pattern. So what actually is happening here is it's pattern matching, but it's executing some weird random code you can write during the pattern match. So for example, for this is character pattern match, it actually uses this function we define here. So it's the same pattern name. This is called the active recognizer, but it's a fancy term for saying this is the function that will be executed when you match on this case. And in here we just like try to parse the line with the regex for a character rule. So it's rule number, semicolon, and then a character between quotes. So if this parses, then we know it's a character rule. So we parse it, or we extract the values, the rule number and the rule, and we return sum. And this is how we tell the matching or the pattern matching that like, okay, this is a successful case. So you can you don't have to look at the next case in the pattern match. You can stop, and this is the deconstructed value. So if you look at this here, this is what we get out of it. So the rule number and the character. And you can do this for all the cases, which is what I did. And yeah, so that's parsing. It's a really cool way to declare string parsing, for example. And that's one of the use cases for active patterns. Fun tidbit. These operators here, or this sequence of this sequence is called a banana clip. So it looks like a banana, and I don't know of any language which has a banana clip in its formal specification, but F# does. So cool. But anyway, we can parse our rules into abstract syntax trees, or like into these types, I mean. Next step we have to do is see which messages apply for which the first rule was it 0 rule. Yeah, so this is the algorithm. It's saying parse my input. That's what we just discussed. For part 2 we can't use the raw rulebook. We have to update some rules, so we update rule 8 and rule 11. Then we find the 0th rule, or rule 0, and then we find how many of the given messages this rule applies to. And this is where we kind of write an evaluator again. So let's go take a look at this applies function. And applies just says like, okay, try to run this rule, or try to run this rule on the message. And if we get a parsing result okay, where we nibble the entire string, so where all the pac-mans ate the entire string, cool, this matches. And otherwise, if it's an okay thing, but we have some remaining A's and B's in there, that's not okay. And when the parser really fails with an error case, that's also not okay. And parses is a bit tricky because it's a mutually recursive function thing, but does it fit on a page? It doesn't fit on a page, but it almost fits on a page. And oh no, it doesn't. But it's basically, this is the parse function, and it says, okay, if the rule is a car rule, let's try to apply the car rule, otherwise the character rule, sorry, otherwise the alternative rule, otherwise the sequence rule, and I defined them separately here. So let's take a look, for example, at the parser for characters. It's given a message and the character. If the message starts to the character, cool, the pac-man consumes this character and it skips it for the remainder. So this is the output of the parser. And otherwise we have a parsing problem, so we fail. I'm using a result type here. So it's either okay or an error. And I think I defined the type, yeah. So this is my result of a parse. It's either the remainder of the string, sorry, that's this, or it's a parsing problem. And you see list here, and this is what took me, I think, 2 hours to figure out. I'll get to that when we look at the other parsers. But that's how applying or parsing a character works. Then a sequence is a bit of the same. So if we have to parse a sequence rule, we just look at a pattern match on the rule, and if it's empty, then okay, we nibble nothing and we return the message. Otherwise, we run the first rule in the sequence, the first parser. So this is called the first result here. So this is where the recursion and the mutual recursion enters. If there's a problem, we stop, because the sequence, every parser in the sequence must do something, and otherwise we have a remainder, we just run the next parsers in the sequence, so that's the RSs on the remainder. And there's some funky stuff going on with maps and reduce, but we'll get there right here, because this is what took me half a day to figure out. And it is if you are running a parser for the OR, so for the pipe, the alternative, I just do it as, okay, run every alternative as a parser for a sequence, so that's just converting this to run this. But I thought in the beginning that if you do a parse of, or if you run a parser that does OR, if the first part matches, okay, forget about the second part, we can continue. That is a wrong assumption, because if the first part matches but somewhere and it returns a remainder, it can be that the second part also matches and returns a different remainder. So that's a bit like backtracking. There's two paths we can take where this alternative rule succeeds, but it ends up with a different string where the rest of the parsers have to match. So this was, yeah, I spent a lot of time figuring this out. But once you do, it's fun, and it's a fully generic parser that can run anything. I don't have to do the crazy shortcuts, specifically for rule 8 and 11. It just works. And as you can see, I had to write a lot of tests, and that's when this happens during Advent of Code, I know I'm in deep. But I had a lot of fun. It took me a bit longer than usual, which is why you're getting the short and abridged version of it, but fun puzzle. I do hope, however, that we've seen enough parsing or parser or grammar puzzles for this year, because I kind of had my fill. I hope you had fun, and I'll see you tomorrow.